So we're going to move to chapter 5 and see why we care so much about the antiderivative. There was one slide at the end that you can look at, but it's okay if we don't go over it. The end of 4.8. And so we'll see how far we get today. We probably won't make it through all of this today, and then we'll pick back up with it next time we have class, which is going to be a week from today. So Wednesday's class isn't happening. Unofficially. Although it's on a recording right now, so I guess. I'm going to be in Ohio. I mean, I could record it, but I won't. Oh, I have these two lost and found items from my office. This is from the classroom. This is my office. Yeah? Okay. My daughter tried to get it, but I wouldn't let her. Okay, let's go ahead and get started. So section 5.1 and 5.3 together make up basically the rest of the beginning of sort of the end. We have this idea that came out of the fact, you remember how we had back in the beginning of chapter 2, we had the tangent problem versus the velocity problem, trying to figure out why we cared about the derivative. And then the area problem is sort of the genesis of why we care about the antiderivative. Here's the problem. I have this function, f of x, which somehow I'm able to get the graph of. Is it working? Is it that loud?
They leak a lot of sound.
Oh, okay. It's going to be deaf. Yeah, good. Okay. Sorry. So I have this graph. I have the x-axis. I want to find the area under the graph and above the x-axis. There's some starting and ending point, x equals a and x equals b. If the function is a line, then it's a familiar shape. It'll be like a trapezoid shape. But most times it's not going to be a line. The graph of the function is going to be usually some curved surface. And so it makes it difficult to find the exact area. And so what we're going to do is make a guess, make a bad guess, and then make the bad guess get better. And so here's a bad guess. Using rectangles to approximate the area. I know how to find the area of a rectangle. It's length times width, or height. And so the height of the rectangle will be somehow decided by the function value. And then the width of the rectangle, I'll just make sure that's an equal width. And so here's a picture of 6 rectangles. And I find the area of these 6 rectangles, and it would be an approximation to the area under the graph of the function. It would be a bad approximation, but it'll be at least a start. Okay? And so that's what we're going to do today. And then hopefully by the end of today, we'll be able to refine this and get a better approximation. That's the idea. Questions about the setting of the problem? Okay? Later on, we'll get more specific. Maybe the function dips below the x-axis and figure out what to do then. But for now, though, we're just going to make a bunch of rectangles, find the area of the rectangles, add that up, and say that's an approximation to the area under the graph of the function. Our first example would be the function y equals x squared, parabola. I'm interested from 1 to 5, and I'm going to make 4 rectangles. Now, for each of these rectangles, I need to decide how I get the height of the rectangle. I'll make sure that the 4 rectangles that I use will have the same width, but the height will be different. And the way I'm going to decide how to get the height will be at each interval, I'm going to choose the right endpoint to go up and evaluate the function. Here's a picture. Actually, this is a bad picture because it's deceptive here. The actual y-axis is over here. This is at 1, 2, 3, 4, and 5. So this axis should be removed, but I couldn't figure out how to make Maple do it for me. So So anyway, the actual axis is moved over, and this is the parabola shifted up 1. Y equals x. Y equals x squared. It's not shifted up at all, and so the actual graph, it continues on here, and here's where the real y-axis is. Okay, and so I take the interval from 1 to 5, and I chop it into 4 sub-intervals, each with an equal width, so they'll each be a width of 1, and then at each interval, I go to the right endpoint, and that's how I get my height. I go up to the function value, and I plug that number in. So this is the function at 2, represents the height of this rectangle, and the width of the rectangle is 1. Then I move to the next interval. I plug in the function at 3. That's the height of the rectangle, and then I get the width. Go to the right endpoint of the next one. That's the height of the rectangle, and then the width. They're all a width of 1. And finally, the last rectangle, I get a height of the function at 5, and then my width is still 1. And so I can add that up. It's not that bad. I'm only plugging it into the function y equals x squared. So I take 2 and square it, take 3 and square it, 4 and square it, and 5 and square it. Each time I'm multiplying by 1, but it's okay. I just don't do that. And so I have a 4 plus a 9 plus a 16 and a 25. And as my picture indicates, that's an overestimate. That's too much. When you add that up, you get 54. And it's too much. When you have an increasing function and you use the right endpoint, each time the right endpoint will give you an area of a rectangle that's bigger than the area underneath the function when the function is increasing like this. But it's somewhere to start, and we'll get better. Questions on the execution of this approximation? Yes?
You know how it's the width is 1, 2, 3, 4, 5?
Uh-huh.
Is it the first, how come you don't go from 0 to 2?
No, it's not a 0. I'm sorry. That's deceptive. This is y. And so this is y equals 0, but it's not x equals 0. I'm sorry. This graph. The actual, here it is. So here's the origin. And this is 1. So forget about this axis here. I'm sorry. Just ignore this. Act like it's not here. Because the axis is really here. I just couldn't make the computer do it for me. I spent so much time trying to figure it out that I just gave up and just went with this drawing. So this is x equals 1. I apologize about that. And all subsequent graphs will be the same way. Okay, so you can do that. It's reasonable as long as the function that you're plugging into is reasonable to do without a calculator. Okay, but it's a bad approximation, and unfortunately to get better, we just have to choose something else. So maybe we'll choose to do the left endpoint, or maybe we choose to do a midpoint. We're still going to find out that's still bad, and the best thing is to do more rectangles. So let's use the left endpoint this time. Same setup. Once again, the axis is actually over here. The y-axis is actually over here. This is actually x equals 1, and this isn't really here. And here are the different counting by 5 on the y-axis. And this time, I go up on the left endpoint to get the height. So from 2 to 3, I go up at 3. I go up at 2. From 3 to 4, I go up at 3. And the last one, from 4 to 5, I go up at 4. When you have an increasing function and you do the left endpoint consistently, you will always have an underestimate. This is not enough. The area under the graph has these parts included, and the rectangle area sum does not include those. So it's an underestimate. But it's easy enough to do. So we evaluate the function at 1, essentially 2, 3, and 4. And the only reason why we're not worrying about the width is because the width is 1, and multiplying by 1 doesn't change anything. Later we'll make the width something else where we have to worry about it. And so square 1, square 2, square 3, square 4. And add those up. And this isn't enough. So 54? 54 was too much. And 30 is not enough. We know the answer at least is somewhere between those two values. Okay. When you have maybe like somewhere in the first month of Math 104, they take this and they go further. They say, well, let's move away from rectangles. Let's use trapezoids. And so they have a whole section where they continue this on. We stop with just rectangles. And they expect you to have the rectangles down enough that they move right on and don't spend any time on it at all with rectangles. And then they expect you to know what's going on with the trapezoids. And so just so you know what's to come. Okay? All right, great. So now instead, if the left was not enough and the right was too much, maybe in the middle. I can evaluate anywhere I want to. I can pick the height of the rectangle anywhere I want to. So once again, y-axis is here. This is actually 1. So now I'll choose to pick the place in the middle. It seems like the most reasonable thing to do because it'll be over and under, and maybe it'll be more exact. So between 1 and 2 is 3/2. Between 2 and 3 is 5/2. Between 3 and 4 is 7/2. And between 4 and 5 is 9/2. That's where I go up and get my height of the rectangle. So this is using midpoints. We did it with the right, we did it with the left, now we're doing it with the midpoint. And this is going to be the most accurate because whatever it is above will almost exactly cancel out with what it is below. And so we now go evaluate the function at 3/2, which is just squaring 5/2, 7/2, and 9/2. And this should be definitely more accurate, and it's going to be the most accurate. So 9/4 and 25/4 and 49/4 and 81/4, if you add all those up, and you multiply them by 1 officially, so that you get an actual rectangle area, you get exactly 41. 30 not enough, 54 too much, and 41 we're saying is pretty accurate. Not exact. It's not exact. We'll figure out how to get exact later. Right now we're just approximating. Section 5.1 is approximating. In section 5.3 we learn how to get it exact. Questions on this? Okay. The best way to get more exact though is to do more rectangles. Impractical really for me to ask you by hand to double the number of rectangles, but you could. Or so we could get more rectangles, and then I'll show you a picture that shows the more the rectangles, the better the approximation. Any questions about what we've done so far? Yes?
When you're using the midpoint of the x value,
Yeah.
where are your
See, it's just a tool to get the height of the rectangle. So the height of the rectangle is judged by how high the function is at these places. Your actual rectangle is on that interval, the width, and then that height. So your rectangle looks just like this.
okay, so this is just to get a different height.
It's all about getting height of the rectangle. The right was using the right endpoint to get the height. The left was using the left endpoint to get the height. But now we're using the midpoint to get the height. Okay? Okay, I wouldn't ask this by hand, but here it is on the computer. If I double the number of rectangles, I'll get more accurate. Let's say we go back to right endpoint and we use 8 rectangles. It's still too much, but it's not. Let me go back to when I had 4 with right endpoint. Where is that at? Oh, geez. Sorry. So see how much it is off here? And what I'm doing by doubling the number of rectangles, this amount that I'm off comes down, and it's not as much. Let me go back to 8 rectangles. And so it's not as much. This much that, the sum of those overages is much less than the sum of the previous overages as far as area goes. Okay? And once again, the rectangles are now going to be not length width of 1. Now, if I go from 1 to 4, 1 to 5, sorry. If I go from 1 to 5, here's how you figure out how wide the rectangle is. Go from 1 to 5, go from A to B, right? So that figure out how long that is. So basically B minus A. And then divide by how many rectangles you want. N is the number of rectangles. So 5 minus 1 is 4. 4 divided by 8 is a half. So each rectangle is a width of a half. So now we worry about it. And once again, y-axis here. This is actually 1. And forget about these numbers here. And so where do I evaluate my first one at? I'm looking at the interval from 1 to 3 halves, and I use the right endpoint. From 3 halves to 2, and I use the right endpoint. Uh-oh. Uh-oh. I confused it. Too many inputs at the same time. Uh-oh. Oh. All right. Too much calculus for the computer. I don't have to reboot all the way, thank God. I just have to get rid of this program and get back on. It's actually going to reboot itself. So here it is with 4 with the right endpoint. Here it is with 8 with the right endpoint. Okay, and then here's the calculation. You know, I don't want you to do this, but you take it at 3 halves, you take it at 2, 5 halves, and at 3, 7 halves, and at 4, 9 halves, and at 5. 8 different evaluations of the function, but each time now, the width of the rectangle is a half. So what you could do is factor all those halves out, and then just deal with that sum. It'll end up as 95 once you add those up, and then divide by 2 to get 47 and a half. So using more rectangles, I'm able to increase my accuracy. Okay. I wouldn't have you do that by hand. That's unreasonable for me to ask. But we can increase even more. Here's the picture with 10 rectangles. This is with 20 rectangles. Notice how much it is over and how that decreases as we, and I have them sort of right on top of each other. 10, 20, 40, 80, 160. As the number of rectangles increases, the accuracy increases. And so what we're going to do is come up with a way to do it exactly, though. This is in, you can't ask someone to do this. Even with the computer, it's too much. And so we have to come up with a way to do this where it's not so intensive. So hopefully that. Okay. So n is the number of rectangles is going to infinity. As n goes to infinity, then the accuracy increases, and you'll get exactly the right area. This is a question from, this is a question from some final exam. Let me eliminate this here. And let's work it out together. Now, we don't know these symbols yet. I apologize, but maybe we should come back once we know the symbols. Yeah. Let's come back once we know these symbols. This symbol there will be explained in the next slides. This is out of order. I apologize. But we'll be able to come back and do this problem, approximate using 4 rectangles, the area underneath this curve. But these symbols here are foreign to us right now, so I should wait for this. I apologize. We'll come back to that. In section 5.3, they introduced the symbols, and they introduced how to do it. Okay, so here's what the symbol means. We were letting n get very large as the number of rectangles goes to infinity. If we take the limit, now what this is here represents the height and the width of each rectangle. Delta x, remember that calculation we did? B minus a over n, that's the width. F of xi star is just some generic way of saying I have to evaluate the function somewhere. Xi star is on the interval where I decide to evaluate it at. Left endpoint, right endpoint, midpoint, wherever I decide to evaluate it at, that's generically called Xi star. So that's how I'm going to get my height, F of Xi star. My width is going to be some calculation that will be not too bad to calculate, but n is going to infinity. And so I'm going to add this is called the summation. This is a summation sign. It's a capital sigma. It means to add up a bunch of things. And this is representative of the addition of all the rectangle areas. Okay? And as n goes to infinity, you'll get this symbol, and it's meant to be the exact area. It's meant to stand for the exact area under the curve and above the x-axis. Between a and b. Okay, that symbol there, that's an integral symbol. F of x is that same f of x, your function value. Dx represents so as n gets big, we saw that the width of those rectangles got very, very small. Infinitesimally small as n goes to infinity. Dx is part of the integrand. You can't just have the symbol, integral symbol, with the f of x without this d of x. It's a necessary symbol, but officially when we end up doing it, it seems like it doesn't play a role. You can't forget it. It's like the plus c. You have to remember it. This is a small width, an infinitely small width of the rectangle. And then this represents the height of the rectangle. And so we are still talking about the area of the infinitely many rectangles, but with this symbol stands for the exact area. No more guessing. This is the exact area. Of course, the limit has to exist. You can't just put a limit if it doesn't exist. If it does exist, the name of what we call the function is integrable. Like we had, if you could take the derivative, it's differentiable. If you can take the integral, it's called integrable. Okay. You can find the limit. Now, the problem is this. We spent a lot of time, maybe a day, a whole lecture, on doing the derivative from the limit definition. Okay? We're going to spend significantly less time doing the integral from the limit definition. Okay? We do not want to do it this way. If you thought doing the derivative from the limit definition was bad, it's much worse to do the integral from the limit definition. But this is it. This is the limit definition of the integral. Okay, the limit definition of the integral. Okay, we'll see why it's called a definite integral and not something else in a second. Okay, but that's all the parts. And remember the goal, though, is to be able to find the area underneath the curve and above the x-axis between some a and b. To find the exact area. That's what that symbol stands for, the exact area. Okay, so you take your interval, you partition it up, and you get some sample points, you get some xi stars to where you're going to get your function at, but you let that go to infinity, and you're able to find the exact area. I'm going to do it once, just so you can appreciate the shortcut. Okay, I can't just go right to the shortcut. Okay, but just know that you will never be asked to actually perform the limit definition of the integral. Like I asked you to perform the limit definition of the derivative, that was reasonable. It's unreasonable, I feel, in this class, to ask you to perform the limit definition of the integral. Okay, you should see it though. Okay, so here it is on an example. Yeah. Okay, so yeah. All right, I have to do this. Just bear with me. There's a whole section on this, which is skipped for us essentially. This is me spending 10 minutes on section 5.2. That summation that we have officially is called a Riemann Sum. Okay, and I'm gonna do it an example like this, not the example that we had, but I'm gonna do an example like this, and I'm gonna walk you through it. If you get nothing out of the next 10 minutes, that's okay. If you write nothing down for the next 10 minutes, it's okay. You can just download the notes afterwards and look at it. I just want you to appreciate the what's coming next, the sort of shortcut to how to find it. Like we had shortcuts to find the derivatives by doing all the rules. We're gonna have some shortcuts to find the integral, and so we need to appreciate the shortcut. So what we do is we take the interval from a to b. Okay, this interval goes on, and we chop it into many subintervals. The way we get the definition of the subintervals, we add delta x repeatedly. So the first one is called x naught, and then x1 and x2 and x3 on, and this one is called xi. Let's say we decide to use right endpoints. That's not spelled right. Sorry. Okay. Let's say we decide to use right endpoints, and with nothing to say we have to use right endpoints, we can use left endpoints or even midpoints. Okay, so I take and I evaluate the function of each of these guys, and I have a delta x, and then there's a limit. So this summation, this dot dot dot, this is an infinite sum because n is going to go off to infinity. But instead of writing the summation, I wrote out a bunch of terms, and what I'm going to do is have the x, all the different x's, replaced by the symbol xi star. Okay, xi is as above a plus I delta x. That's the I one that I go and evaluate the function at. Delta x is b minus a over n. And so if I take a plus I delta x, that's going to be where I have to go and plug into the function. That's going to be my xi star. A plus I delta x. And then that's multiplied by delta x. Okay. So xi is xi star, and xi looks like this. Now delta x looks like this, so I get this guy being xi star. And then it gets multiplied by delta x, but delta x has no has nothing to do with the summation, so I'm going to pull it out of the summation. Okay. All right. What I need to be able to do this is how to add up a bunch of things. If I add up 1 n times, I'll get n. If I add up 1 plus 2 plus 3 plus 4 plus 5 up to n, I'll be able to get this formula. The sum of the first 100 numbers is 100 times 101 divided by 2, and so on. And so the sum of the first squares, if I take 1 plus 4 plus 9 plus 16 and on, and I stop somewhere, I can plug it to this formula to figure out what it is, and cubes. So there's a whole section on this. This is section 5.2, and we have to use these summations to help us figure out the actual limit definition. Okay. So I'm sorry. Let's go back to our f of x equals x squared, and we'll do the limit definition. We have exactly this symbol here, And that's the hard part, trying to figure out what's going on with that symbol. This is the exact area. Now we know what that symbol means, the exact area. And this is the Riemann sum. And we're going to perform this limit. We're on the interval from 1 to 5. So b minus a is 4. And a plus delta x times I is, delta x is now 4 over n. So I take 1 plus 4 over n times I. What do you do with that? You take and you plug that into the function. What's the function? The function is x squared. So I take this inside and I square it. Take 1 plus 4i over n and square it. So you get 1, you get 8i over n and 16i squared over n. And we take each one of those separately. The sum of 1 using the table on the previous slide, the sum of the I and the sum of the I squareds. The n's, you can pull them out of the summation. The summation is based on I. Anything that doesn't have an I in it can, as a factor of it, can be pulled out. And so from the previous slide, if I add up 1 n times, I'll get n. If I add up I, n times, I get n times n plus 1 over 2. And if I add up I squared, n times, I get that n times n plus 1, 2n plus 1 all over 6. And now I need to do a limit as n gets big. To simplify, I need to pull things out. So let me put this 4 over n back in. And then it'll be, oh wait, I guess I've already done it there. Sorry. You put the 4 over n back in, cancel what you can. Cancel what you can. Multiply out. In the end, you want to get some fraction, and so if I divide everything by n squared over here, I get these 3 terms. I divide everything by n, I get these 2 terms, and I still have this 4 floating around. Now n gets big, so anything with an n in the denominator, I can do the individual limits. These guys all go to 0. And I'm left with 4 plus 16 and 64 over 3. Add those up. You get 124 over 3. Exactly 41 1/3. That's the exact answer. But that was too much work. Now I went through it rather quickly. Expected not to have any questions because I don't want you to have to worry about that. You should see it though. Okay? There's a better way. We don't have to do it this way. So we saw the approximation. We saw the limit definition way to do it. We need the shortcut way. Because that's the way you're going to do every problem. I mean, I might have you, do some approximation. We're going to go back to that question and do the approximation. But I will not have you do this limit definition way. You need to see it, but I will not have you do it. Okay? All right, so let me go back to that previous slide. Let's practice an approximation question. And then, if we have time, let's see how we actually do it. This isn't the most efficient way to do it. Now we'll come back to this slide too. Oh man, where's the example at? Where's that example slide at? Oh, right. It's All right, so this represents the exact area. We're not going to do it by limit definition. We're going to do it by approximation. They're asking us to do it by approximation using 4 rectangles. You have this interval from 1 to 5, 4 rectangles. Conveniently, that's cutting it into rectangles that have a width of 1. Using left endpoints. So each time I get an interval, I need to evaluate the function on the left. So I take the function at 1. Then next interval, I take the function at 2. Next interval, I take the function at 3. And the last interval, I take the function at 4. But what do I do with these guys? I have to multiply them by the width, which is officially a 1. And these are my rectangle areas. What do I do with these guys? I add them up. and that's my approximation. This symbol is the exact, and this is my approximation. We'll see why it's reasonable to ask you to do this by hand, because the function f of x is 2 minus x over x. So plug in a 1. What do you get? 2 minus 1 over 1? 2 minus 1 over 1? That's okay. 1 over 1? Okay, how about 2 minus 2 over 1? Okay, good. How about 2 minus 3 over, I'm sorry, 2 minus 2 over 2, sorry. 2 minus 3 over 3. Negative 1/3. Okay, finally 2 minus 4 over 4. Negative 1/2. Wonderful. All right, what are you supposed to do with these guys? Times them by 1. Really not doing anything there. Add them up. So we're getting a 1 plus nothing minus 1/3 minus 1/2. So it's reasonable by hand. It's reasonable by hand. Okay. Make it all over 6. 6 minus 2 minus 3 all over 6. We're saying that the area is approximately 1/6. All right. So if I give you this symbol, that's the exact area. But then I have to give you directions of how I want you to approximate it. I tell you how many I want you to use, and I'll tell you what method I want you to use. Okay? But we won't spend much time there with approximating when we know how to do it exactly. Not by definition, but by a shortcut. Let's talk about the shortcut. Okay, shortcut is officially, the fundamental theorem of calculus. Officially, it's part 2, though. We'll get to part 1 later. So that's very important, right? There's nothing that says more important than the fundamental theorem of the class that you're taking. Right? If you write nothing down all semester, you probably want to write this one down. The fundamental theorem of calculus. Connecting derivatives and antiderivatives. It says this. If you want this symbol, if you want this area, please don't do limit. Please don't do a limit definition. Instead, if you can do it, here's a problem. If you can find the antiderivative, if you can do what we were doing back in section 4.8 on Friday, if you can find the antiderivative of that function, then all you need to do is plug in the upper endpoint to that antiderivative, plug in the lower endpoint to that antiderivative, and subtract those two things. The hard part is finding the antiderivative. But if you can do it, fundamental theorem of calculus says this is how you're going to get the exact area. This is the shortcut method. Okay? So our problem was from 1 to 5 x squared. We like the exact area. Fundamental theorem of calculus says, okay, find the antiderivative. Go back to section 4.8. 1/3 x cubed. Antiderivative of x squared is using the power rule in reverse. You add 1 to the exponent and you divide by exactly the same thing. So the antiderivative, call it capital F, is 1/3 x cubed, if you want x cubed over 3. Fundamental theorem of calculus says, you know what? Take that, f of x, and plug in a 5, plug in a 1, and subtract those. The function needs to be continuous for us to do that, and x squared is continuous. Okay, so 5 cubed over 3 minus 1 cubed over 3 is the exact answer. No messing around with rectangles, no messing around with limits. Exact. Quickly. Okay. 125 over 3 minus 1 over 3. 5 cubed, not 5 squared. 5 cubed. So we get 124 over 3. Exactly the answer that we got doing the limit definition in under a minute. So you need to appreciate, so now we can appreciate how wonderful this is because we did it the long way. So it goes back to being able to do what we did on Friday, find the antiderivative. And algebra, evaluating an antiderivative. Question, yes? When you need to add a capital C. Very good. So if I were to put a plus C here, and a plus C here, the plus C and the minus C would have canceled out. So I just say, don't bother with it. If it's always going to cancel out, it's not a different C, it's the same C. So technically, this plus C is involved, but it gets added on and then subtracted off, so why bother with it? Good question. More questions? All right, maybe what was that? 2 minus x all over x. Okay, let's try that one. Let's see if we can do this one. It was 2 minus x all over x. The other example, from 1 to 5, 2 minus x all over x. We need an antiderivative of that guy. It's not ready as it is. Okay, there's no reverse quotient rule. Okay, when you ever have one term in the denominator and multiple terms in the numerator, you can take and sort of unsimplify, break it apart into 2 fractions. So we need to do algebra before we can even start. We'll call this 2 over x minus x over x. Which is 2 over x minus 1. All right, let's see if we can find the antiderivative of that. What is the antiderivative of, let's do the easier part. What is the antiderivative of a negative 1? If your function is negative 1, what is your antiderivative? Somebody said negative what? Negative x. Very good. So that part is done. Okay, we get a negative x there. What function has 2 over x as its derivative? When have we ever seen x on the denominator? Why even have headphones on? This is 2 times 1 over x. The power rule in reverse does not work when the exponent is a negative 1. Where have you ever seen 1 over x before? As a derivative of the natural log of x. The 2 just gets carried along. So the antiderivative of this is 2 times the natural log of x. Okay, power rule in reverse does not work here. Okay, almost done. So we get 2 times the natural log of x minus x. That's our antiderivative. We need to plug in a 1 and a 5. This symbol means I am about to plug in a 5, and then I'm about to plug in a 1, and then I'm about to subtract them. That's what that symbol means. So we get 2 times the natural log of 5 minus 5. We get 2 times the natural log of 1 minus 1. Plug in a 5, plug in a 1. Now, the natural log only has that part in it. It's not like the whole thing minus that. It's just the thing that was plugged into the log. Later, you take away 5. Later, you take away 1. What is the natural log of 1? 0. So that part zeroes out. And when you subtract a negative 1, it's like adding on 1. So the exact answer to this question is 2 times the natural log of 5, and then you subtract 4 from that. That's the exact answer to that question that we were trying to approximate. Okay, that's enough for today. We have more gaps to fill in. We'll enjoy your Thanksgiving break, and I'll see you when you get back. Have a safe trip if you're going somewhere.
Did I do that? I don't know.